Day 6 was also really cool. It's all about trying to win a bunch of toy boat races, where the toy boat starts out in a charging station, and we can control how long the boat stays in the charging station. And once the boat starts moving, it'll move at a constant speed, which is equivalent to the time it spent charging. So if it waited for 5 units of time, it'll move at a speed of 5 units of distance per unit of time. So there's a compromise here because each game is limited in time. The first game is limited by 7 units of time, 15, or 30. Um, so we want to move for as long as possible, but we also want to move as fast as possible. And now the question is, for each game, there's a corresponding distance that we have to beat. For the first game, we have to beat a distance of 9. Let's think about this. If we wait for 1 unit of time, then we can move for 6 units of time at a speed of 1. That's a distance of 6. So we don't beat the distance of 9. If we wait for 2, then we can move at a speed of 2 for 5 units of time. So we get a distance of 10. So here we actually beat the game. If we wait for 3, we also beat the game with a distance of 12. And now it's interesting, here it gets symmetrical. If we wait for 4 units of time, it's the same score as if we waited for 3 units of time. This is because the curve is actually a sort of parabola where the center is exactly at half of 7, which is 3.5. So if we wait for 5 units of time, it'll be the same score as if we waited 2 units of time. Here it might be helpful to actually visualize this on a graph. So I wrote down the function that calculates how far we can travel given a certain total time for the race and the speed that we gained through charging the boat. So let's say the total time is 7 and the speed would be 2 because we waited for 2 units of time to charge the boat. Then we would have 7 minus 2 time left. This is the time we have left, 5 units of time, times the speed, which is 2. So we have 5 times 2 is 10. And we see that right here. If we wait for 2 units of time, then we have 10, a distance of 10 in the end. And here we can also see how this beautiful symmetrical shape comes out of it. So if we wait for 0 or 7, it's the same number, it's 0. If we wait for 1 or 6, it's the same number, 6. If we wait for 2 or 5, then we get distance of 10. If we charge for 3 or 4 units of time, we get a distance of 12. The red line is how far we need to travel to win the race. And here we can see there are 4 winning options and 4 losing options. So here we have 4 distinct ways to win the race. We can either wait 2, 3, 4, or 5 units of time, and we'll beat the distance of 9. We have to calculate this number, the different number of ways to beat the game for each game, and then multiply those numbers, and we get the answer. So let's solve the first one in a completely brute force way. So as always, the first part is to parse the input. We separate out the distances and the times here, and we map them to integers. I like to use regular expressions to do this. And then we zip the time and distances because we want to have them as pairs. Then we initialize a variable called total, which will keep track of the final product. And then for each race, we'll have a variable called wins, which will keep track of how many distinct ways there are to win this particular game. We'll iterate through all the possible speeds, calculate the final distance through the formula mentioned earlier, and if this distance is greater than d, then we add 1 to our wins. We add this number of wins to the total, and there we get our answer. So this is it. We can add a little optimization here as well. We break the for loop once we reach the downslope and are no longer winning. And that's it for part 1. The idea behind part 2 is pretty straightforward. Instead of viewing this as 3 different games, we view it as a single game where we concatenate all these numbers. So the time for this game will be this number right here, and the distance we need to beat is this number. So obviously we could take the same exact approach and we'll try it out. So first we change the way in which we parse the input. By using the join method, we can join together all the numbers to form a big number. We use an empty string as a separator, so there's no spaces between the numbers, and then turn this number into an int. We do the same thing with distances, although now it's no longer distances, but distance, so only one. And then we'll see how much of this code we can reuse. We skip the for loop, we just have one number now, and one total called wins. We'll just rename some variables here. Maybe we'll call the calculated distance final distance, and the distance we need to beat, we'll call that target distance. So if we decide to run this, and we actually return the wins variable, we can see that it works. The problem is not that it doesn't work, the problem is it's pretty inefficient. It works pretty well with the example input, but once we use our own input, for me it took 20 seconds with this code, which is suboptimal. So now we're going to explore a second option of how to solve this problem using math. Let's return to our graph from before. So what we did earlier was we did a for loop of 0, 1, 2, 3, 4, 5, 6, and then calculated the corresponding y value and looked if is it above the red line or is it below it. If it's above the red line, then we won the game. Otherwise, we lose. And we counted 4 dots above the red line. Now let's use a more efficient approach. Instead of a for loop, we simply jump to this spot where the possibilities meet the requirements. And since this is not actually a possibility, we can't use floats, we have to use discrete numbers. This is the actual first possibility that's above the line. So we calculate the distance of this x value from the origin, which is 2, and we subtract 2 from the total number of possibilities. So from the total number of possibilities, 2 are not viable. On the other side, we see the same thing. For symmetry reasons, we only have to do this on one side and simply multiply by 2. So we take the total number of possibilities and subtract 2 times 2. Total number of possibilities is 8. We have 0, 1, 2, 3, 4, 5, 6, 7. 8 minus 2 times 2 is 4. So this is how we get our answer. Now let's see how we get the formula to calculate this spot right here. The easiest way to get the formula we need is to use Wolfram Alpha. So this was the formula we had to calculate the distance, t minus x times x, where t is the total amount of time for the race and x is the amount of time we spend charging our little boat to go faster. And this equates to d, the total distance that we travel. Now let's say we solve this equation for x. We want to know what is x as a function of d and t. We get 2 answers for this, that we see it down here. And we should get 2 answers because the line crosses the parabola at 2 points. And this will be the lower one, and this is the higher one. We see a minus here, and we see a plus here. So we're interested in the lower one. We only need one, remember? And what we do now is we plug in the t and the d from the puzzle input. So we know exactly how long should we accelerate to exactly reach the required distance. Let's put it all together in Python. First, we import this formula to calculate the exact x at which the possibility curve meets the requirements line. This x will be a float, and we want an integer. We want the next integer. We can't just use the ceiling function, the math ceiling function, because if x float is already at an integer location, we would need the next integer. We couldn't use that integer because we don't just need to meet the requirement, we have to exceed the requirement. Here we see that if we use math ceiling on 5.0, we get 5, but if we get int of 5.0 plus 1, we get 6, so that's why we use int. And now we can get our answer by taking all the ways to play the game, which is time plus 1, minus all the ways to lose the game, which is 2 times x int, and the answer is all the ways we would win the game. There you go, this is the math solution, which is way more efficient than the for loop brute force approach. This one took just a couple of milliseconds, whereas the other one took 20 seconds. So, big improvement. That's it for part 2. If you're also a big fan of Advent of Code and it's helping you to learn to program, as it helped me, you might also enjoy visiting my website where I keep all the solutions I've got so far, presented in an interactive and hopefully appealing way, as well as other fun stuff. See you there.